Tech Talk webinar. Today's Tech Talk is sponsored by the New Jersey Bureau of Research, New Jersey DOT Bureau of Research, that include webinars, lunchtime talks, and other events. Tech Talks are meant to share and promote the implementation of research and innovative practices and the transfer of knowledge among NJDOT staff and others within New Jersey's transportation industry. Today, we are pleased to have Scott Douglas from the Office of Maritime Resources at the New Jersey Department of Transportation give a talk on dredging, dredged material management, and the New Jersey Marine Transportation System. Scott will speak for about 50 minutes, and then we will have about 15 to 20 minutes at the end.
I'm like, wow.
We will try to break around 1:15. To submit a question, please use the bottom right chat box marked Q&A and submit all questions to the host. Questions will be addressed following the presentation. Professional development credits, or AICP maintenance credits, are available if you stay for the full session. Your name will be included among those, your name must be included, among those who registered today. Also, please complete a feedback form that should pop up after the event. Your feedback is important to us, so we would greatly appreciate that. Okay, with that out of the way, I'd like to introduce our speaker today. Scott Douglas serves the state of New Jersey as the Dredging Program Manager for the Office of Maritime Resources in the New Jersey Department of Transportation. He's responsible for crafting dredged material management strategies statewide. His duties include management of maintenance dredging and beneficial use projects in the New Jersey State Channel Network and management of projects demonstrating dredged material beneficial use technologies, as well as crafting new policies encouraging domestic waterborne commerce. Scott Douglas graduated from the University of Vermont in 1989 with a master's in environmental toxicology. Prior to joining NJDOT, he worked for 2 environmental testing firms in northern New Jersey, where he honed his expertise on toxicity testing and identification, among other activities. In seminars more than 24 peer-reviewed articles. He is also an adjunct professor in civil engineering at Rutgers for their Maritime engineering program. Okay, with that, we'll turn over the controls to Scott. Thank you.
All right, thanks, Diane. Appreciate that, and I appreciate everyone giving me the opportunity to interrupt your lunch hour. Thanks for logging in. Certainly, anybody who does log in, though, please mute your phone. We're getting some strange, interesting sounds coming from across the web there. Before I start, I just want to acknowledge that this presentation is going to cover what has been happening in dredging and dredged material management in New Jersey over the last 25 years, and as a result of many people working creatively, not just at the Office of Maritime Resources, but across many agencies and states. And I couldn't begin to list all of those who have worked with me and contributed to what I'm about to present, but I especially want to thank all my colleagues at the Office of Maritime Resources, past and present. It's been a wild ride. The audience today ranges quite a bit in experience, knowledge, and interest area, so I'm going to apologize up front for those of you who are left after today wanting a bit more. If this is review for you. We're working hard right now to update our website, and hopefully soon you'll be able to go there to obtain more information. And you can always reach out to me with your specific questions and concerns as well. I'm always willing to talk about dredging and dredge material management with anyone. So let's get right at it. I'm going to start with an overview of our marine transportation system, and then give you some insight into maritime engineering and dredging construction. But most of the talk will be about dredge material management, arguably the most complicated and potentially controversial part of what we do, and it's where I've spent most of my time and energy. I'll end up, close out with a few case studies, just to show you what we're working on. Now, forgive me while I figure out how to use all the controls here, but there we go. So starting out with the marine transportation system. Most of you here today are probably working on the land side of our transportation infrastructure, maybe air or rail. And while maritime transportation is the oldest and largest of our transportation systems, it is less visible and has fewer people working in it than the other modes. According to the Maritime Administration at USDOT, the Marine Transportation System, or MTS, consists of waterways, ports, and intermodal landside connections that allow the various modes of transportation to move people and goods to, from, or on the water. The Marine Transportation System spans the globe and connects the world's major commercial hubs through the world's oceans. The Panama Canal and Suez Canal were significant early engineering improvements that ensure that there's a seamless flow of maritime commerce around the world. Historically, all commerce in the New World was conducted by water. As our country grew, it capitalized on extensive natural water courses and access to both the Atlantic and the Pacific Oceans to solidify its status as a global economic force. Today, the MTS in the U.S. contains over 25,000 miles of engineered waterways, connecting 300 seaports and over 3,700 marine terminals to the global marketplace. More than 13 million people today owe their jobs to the MTS, and it contributes about $750 billion annually to our GDP. It is not a trivial mode. New Jersey itself is truly a maritime state. We have over 650 nautical miles of engineered waterways servicing 2 international ports, a world-class fishery, and a multi-billion-dollar recreational shoreline that contributes over $50 billion annually to the New Jersey economy. The U.S. Army Corps of Engineers and the Port Authority of New York and New Jersey manage the deep draft navigation in and out of New York Harbor and the Delaware River, as well as the 100-mile New Jersey Intercoastal Waterway that connects our back bays to the Atlantic Ocean. The NJDOT is responsible for the operation and maintenance of approximately 200 nautical miles of state waterways, providing the critical link between those federal channels and the numerous municipal and local channels and private berths. So just what does this NJMTS look like? Well, it varies considerably across the state. From facilities as simple as this South Jersey boat ramp to state-of-the-art, fully automated container terminals like this one in Jersey City. Our waterways vary too, from relatively simple channels, small and shallow for recreational boating, to complex arrays of access channels into, like this one, this set, into and out of the New York, New Jersey harbor that provide safe navigation for container ships as long as 3 football fields. These particular channels took decades to construct and cost billions of dollars. Engineering channels like these can even require our ship pilots to use simulators, much like airline pilots. Oops, wait a minute, this one has animation that's not working. Okay, well, there's a picture of a simulator. But basically a simulator, much like an airline pilot would learn how to use a new aircraft or new procedure in an aircraft by using a simulator, our marine pilots actually use simulators to evaluate engineering, design, and navigability of channels. And while the engineering of navigation channels is a fascinating area in itself, it's a topic for another day. For the rest of the hour, I want to focus on their construction and maintenance, which is what I've spent most of my career doing. A navigation channel is an engineered waterway that has been constructed to provide a road to safe navigation from one location to another. The width and depth of the channel is dependent on the location, the type and number of vessels that will use it, and the wave and wind conditions typically encountered. In most cases, the channel will require the removal of some amount of native material from the bottom, in other words, dredging. The amount and type of material can vary from loose mud to hard rock, and over time, Mother Nature will try to fill the channel back in, so periodic maintenance is required to keep the channel safe for vessels to traverse at all stages of the tide. Just like our highways, there are different types of channels and different agencies charged for their construction and maintenance. The main access channels from the ocean to our harbors are federal, analogous to our interstate highway system. The U.S. Army Corps of Engineers is responsible for those. The state is responsible for providing access from local facilities to the federal system, much like our state highways. In the ports, that responsibility falls to the Port Authority, but in the rest of the state, it falls to the NJDOT. But wait, there's more. Local municipalities and homeowners are responsible for providing access to the state channel network from low volume, low use, and residential lagoon communities, much like our local and county roads do. And then there are berths and terminals, which are much like driveways. Responsibility for dredging these falls to the landowner. Channel work of any kind starts with a condition survey. Unlike roadways, a visual inspection is not possible. We use specialized sonar equipment to survey the bottom in the vicinity of the channel, and the data collected are modeled to illustrate the location, extent, and volume of shoaling. Once it has been determined that the shoaling is a threat to safe navigation, it is necessary to carefully evaluate the nature of the sediment that needs to be dredged. In New Jersey, this means that the NJDEP, the New Jersey Department of Environmental Protection, will approve a plan to sample and test the material. Using the bathymetric survey, a number of samples will be designated and taken to provide a good representation of the material to be dredged, usually one sample for every few thousand cubic yards. This sediment is then subjected to a variety of tests. Exactly what test depends on two things: the location and what we intend to do with the material once it's dredged. If the project is located in an area known to be contaminated, like Newark Bay, for example, then the chemical testing required is extensive. If the material is likely to be clean sand, then less testing is required. If the material is destined to be placed in the open water, then complex biological testing may be required. If the material is destined to be placed in a confined upland site, perhaps less rigorous evaluations are required. The samples are typically taken using a vibrocoring device, and the cores are examined by a geologist. This information is used by the New Jersey DEP and the U.S. Army Corps of Engineers during the permit process. The contractors also need this information to provide qualified bids for the dredging work. The sediment is sent to laboratories experienced with the specialized chemical and biological testing required. The material can vary widely depending on the location and whether or not the channel is new or being deepened, or it's simply a removal of shoaled material. New construction and deepening usually involve the removal of consolidated clay and rock, while maintenance is usually limited to unconsolidated sand, silts, and clays. Once a permit is obtained to do the work, you need to have a good dredge. Dredging equipment will vary with the job. Deep draft navigation uses very large marine equipment to efficiently remove millions of cubic yards. Dredges can be hydraulic or mechanical. Hydraulic dredges dislodge and vacuum pump sediment in a 10% slurry. The slurry is either placed into an onboard hopper or transported to the disposal site via pipeline. Mechanical dredges, on the other hand, are either crane-mounted buckets or excavators used in conjunction with scows. In contaminated areas, specialized bucket dredges are used that minimize resuspension of fine-grained material, which can spread pollution. Shallow draft navigation dredging requires smaller equipment. In New Jersey, cutterhead pipeline dredges have been the equipment of choice for many years. However, dredging operations near shore or in very tight, shallow areas often is performed with mechanical equipment. I like to think of dredging in New Jersey as having three distinct flavors, and we can divide these into regions: the New York, New Jersey Harbor region, the Delaware River region, and the Atlantic Shore region. In the New York, New Jersey Harbor, we mechanically dredge 1 to 2 million cubic yards every year of moderately to highly contaminated fine-grained material, and about the same amount of clean sand, gravel, and clay. The projects are large, and so are the price tags, but this is pretty much accepted as part of doing business in the third largest port in the country. On the Delaware River, even more material is dredged every year, but here the dredging is primarily hydraulic and into very large federally owned confined disposal facilities. Explain what those are in a bit. Costs and volumes of jobs are moderate for New Jersey, even considered routine. However, recent experiences with the Delaware Deepening Project spawned disagreements over the equipment and dredge material management techniques used, and what has worked so well for many years may not be acceptable tomorrow. Fortunately, agencies and stakeholders have been talking extensively about ways to ensure that the needed improvements in maintenance will continue to be performed. The third region, and the one that NJDOT has the largest role in, is the Atlantic Shore region. Of the over 300 miles of engineered waterways in this region, about a third is the federal intercoastal waterway. The rest is either state or municipal responsibility. Projects are typically small, less than 50,000 cubic yards. The material is clean, and it has been historically dredged with hydraulic cutterhead dredges and piped upland confined disposal facilities, or CDFs. And yes, we will explain what those are. The economic value of these shallow draft channels typically is only 5 to 7 feet deep, as opposed to 50 feet deep in the harbor. It's not nearly as high, the value of these channels is not nearly as high as the deep draft channels where international cargo is moved. But these smaller businesses that access these shallow draft channels often have more influence on their local communities and consequently local economies. So that's the system and how we maintain it. Simple, right? Except that once we have the material off the bottom, we need to have a place to put it. And that's the hard part. Unlike when I started in this business 25 years ago, when dredged material was still called spoils and was considered a waste, today there are a lot of options. Many of those options were tested and proven right here in New Jersey. The first thing to understand about managing dredged material comes from soil chemistry. Sediment is soil that has been lifted up by rainwater and carried into a waterway where it settles out. If the material is fine-grained, and it settles through polluted water, it will tend to accumulate and hold those pollutants. If the material is coarse and it settles through clean water, it will probably remain clean. The cleaner the material, the more options for use. The second thing to understand is that sediment is a natural part of the aquatic ecosystem. It is necessary to support aquatic life, and removing it from the system is often detrimental to the long-term health of the ecosystem. Sediment is a resource. Here we are. Historically, we just wanted to get rid of it. One of the main options was to place material in a confined disposal facility, or CDF. A CDF is a retention basin designed to hold the dredged slurry taken from a cutterhead pipeline dredge and hold it for at least 24 hours to allow the sediment to settle out. The water level in the CDF, and consequently the retention time, is controlled by a simple weir structure and outfall pipe that discharges the water back to the waterway from which the sediment was dredged. Hundreds of these have been built in New Jersey over the years, but over time, The sites have either been built upon or turned into habitat for wildlife. There are only about 30 of them left in the state that can be used for our program. If the material is coarse enough, it can be suitable for use on a beach. If the material is greater than 90% sand, we can use it on a bathing beach. If it is greater than 70% sand, but often less than 90% sand, we use it on non-bathing or natural beaches. This option is quick and relatively cheap, so we use it everywhere we can. But in places like New York, New Jersey Harbor, millions of cubic yards of sediment requiring dredging is fine-grained and cannot be placed in a CDF because we don't have any place to build CDFs in the metropolitan area. Since the founding of the port, dredged material from the harbor was taken to a location away from the center of commerce and dumped unceremoniously on the bottom. As the port expanded, the location for dumping moved further and further out to sea. In the early 1990s, environmental groups sued the federal government over this practice, and ocean disposal is now only used here as a method for capping the historic deposits placed out there at a site off Sandy Hook called the Historic Area Remediation Site, or HARS. So, if we can't take material to the beach or the ocean, and we have no ability to construct CDFs, what can we do with the millions of cubic yards of contaminated sediment that must be dredged every year to maintain access to our ports? One solution is to place that material upland on sites already far more contaminated than the sediment itself, like landfills. Or even better yet, old industrial sites, otherwise known as brownfields. If this material can be used to facilitate the remediation of these blighted lands, not only will we solve a thorny maintenance problem, but perhaps we can recycle the properties back into productive use. Problem is, this is what maintenance dredge material from New York, New Jersey Harbor looks like. It's primarily fine-grained silts and clays, or otherwise known as fluid mud. It's the kind of material that gives geotechnical engineers nightmares. It's wet, it's difficult to handle, it's difficult to compact, and even if you do dry it out, it doesn't behave well. Most project engineers absolutely refuse to have anything to do with it. And wait, didn't I say it was contaminated too? Well, forget it then. Right? But what if we could make it behave? Mixing it with a pozzolanic agent like Portland cement has proven an extremely valuable technique. When mixed it with about 8% Portland, or the equivalent in fly ash or other materials, what is created is a material that is stackable, truckable, and when compacted becomes a monolith that will not only withstand decades, if not centuries, of exposure without breaking down or leaching the contained contaminants. In fact, it's the perfect capping material for those blighted properties I was talking about. And since we started doing this about 20 years ago, we've successfully dredged and placed millions of cubic yards of contaminated sediment from New York, New Jersey Harbor. How do we do it? First, we dredge it up and transport it to a wharfside facility. Then we allow the sediment to settle for about 24 hours and decant the water right back to the same water body it came from. Then the material is either screened for debris with a rake or put through a grizzly to remove it, depending on the mixing process used. And this isn't a trivial step because in New York, New Jersey Harbor, there can be a lot of debris. The dewatering continues by adding a pozzolan. This can be accomplished in a variety of ways. The Portland cement can be added directly to the barge, as shown here. This technique is typically used when the precision of the mixing is not that important, for things like non-structural fill for a landfill cap. For more precise engineering mixes, a pug mill can be used. And even more sophisticated techniques like pneumatic tube mixing and computer-controlled dosing can be used for highly technical applications. The two techniques have their 3 techniques, 4 techniques, however many you want to take, have their advantages and disadvantages. In-barge is quicker and cheaper, but requires more wharf space. The pug mill, however, is more precise, but it's slower and more expensive. Either way you choose, the product pretty much looks like this in the end. It's considerably different than fluid mud. In most cases, the material has to be left to cure for 24 to 48 hours, but then it can be loaded up and transported. And once it's at the site, it does require some getting used to. It's dark, often still wet, and must be placed carefully in lifts of 6 to 12 inches, but experienced operators can do it quite successfully. And it compacts and grades nicely, making for a very satisfying result. Once filled, these sites have been developed into warehouses, logistics centers, golf courses, parks, and even open space for wildlife habitat. The bottom line, it works, but it's expensive. Prior to the closure of the mud dump, the cost of dredging was about $5 to $10 a cubic yard. Stabilization and upland placement today runs $60 to $80 a cubic yard or more. And there are only so many places where this will work. So what happens when the last contaminated site is remediated? Well, hopefully we run out of contaminated sediment before that happens. But if we don't, we have a plan. Using contaminated sediment as a feedstock to produce value-added construction products like pozzolans or manufactured topsoil or lightweight aggregate has theoretically unlimited capacity. In partnership with the US EPA, the Office of Maritime Resources funded several pilot and demonstration projects of various technologies ranging from thermal desorption to soil washing over several years. And while many of these technologies actually do work, issues of cost, scale, and schedule could not compete with the simple stabilization techniques, and so have essentially been abandoned for now. So that's the story for high volume, deep draft, high value channels. What about clean, small quantity, shallow draft, lower economic value channels? The economic value of access channels to our ports may justify costly methods, but what about these recreational channels? And are those techniques even necessary if the material is clean? As I mentioned before, historically dredging was performed by hydraulic cutter head dredges, and the material is pumped onto the marshes in confined disposal facilities. But over the years, that land has either been preserved for wildlife or built upon. There is precious little left for the management of dredged material. Fully 1/3 of our system has no ready disposal option. The Office of Maritime Resources has been searching for sustainable answers for this region for many years, without much luck. However, in 2012, a little event called Superstorm Sandy changed things. Not only was our office put in charge of maritime recovery for the Atlantic Shore region, but we also found that the people who lived there were suddenly very interested in the resiliency that can be provided by creative management of sediment, either in the marshes or on the beach. The first thing we realized, even before Superstorm Sandy, was that if we couldn't build new CDFs, we were going to have to consider reusing the ones we have. That means excavating the sediment in them and finding a good use for it. And while the concept isn't difficult, most CDFs were not constructed with the idea of removal in mind. Few have access roads, and the material varies considerably in grain size, distribution, and readiness for use, depending on site drainage. However, most of the material is clean, and there's often a use for the material, either as construction fill or landfill cover, or even agricultural amendment. The real issue is that the cost of site and material preparation, excavation, and transport can exceed that of other more conventional sources, which means we have to subsidize it. So we're looking for sites, new sites with good access for new CDFs. And rather than thinking of them as disposal sites, we are thinking of them as permanent management facilities. And we are designing them with more robust berms, permanent weir and input-output structures, with equipment staging areas, and in some cases, loading and offloading docks. We're looking for larger parcels to work with, and we'll be managing them for the long haul. But what about those areas that no longer have a CDF or have no land suitable to build one? We did think about the use of stabilization techniques. However, there are limitations to the end use of that material. And since most of our material is clean and tends to not be as silty as harbor mud, we prefer methods that are more focused on simply removing the water, like mechanical dewatering, using hydrocyclones and belt filter presses, for example. While expensive, this technique can be performed on a small footprint and will keep up with our small hydraulic dredges, so it can be cost effective. A similar technique to use large bags is to use large bags made of geofabric. We usually call them geobags, to passively dewater the sediment. The bags are filled directly with the dredged slurry and the sediment retained while the water drains into a collection point for discharge back to where it came from. Polymers are added to the mix sometimes to aid flocculation for fine-grained sediment and to accelerate the dewatering. This technique is cheaper than mechanical methods, but requires a larger footprint, and you need several months in order for the material to get to a point that it can be trucked. Another technique that resembles something that we've done in the harbor region is to use dredged material to fill underwater pits. Again, Maritime Resources was evaluating this option even before Superstorm Sandy. In a study conducted at the Stockton Coastal Research Center, over 100 underwater depressions were evaluated for water quality and aquatic life use. Many of these depressions are actually subaqueous borrow pits, referred colloquially as dredged holes. The excavated material was used many years ago as aggregate for beach replenishment or construction, but the pit remains. Many were determined by Stockton to be hypoxic or anoxic at least part of the year and devoid of life. Filling them in would not only restore the habitat of the bottom, but it also returns natural tidal flushing, and not the least, from my perspective, providing a home for dredge material. Our survey indicated that there is a potential to manage millions of cubic yards of dredge material while restoring these pits, and we believe at a sustainable cost. One of the oldest techniques in the book is to simply remove the material out of the channel and sidecast it to another location, usually taking advantage of tide and current to dispose of the material, kind of a sweeping it under the rug technique. This hasn't been allowed in recent years, even for the cleanest of material, due to concerns of smothering existing resources. However, in extremely high energy environments like the Hereford Inlet here, it appears that pumping material directly into the outgoing tide does not result in unacceptable impacts. In fact, in a pilot we did in 2018, we found it hard to distinguish the dredge material from the material naturally moving in the system. This technique holds promise for those channels that suffer from rapid shoaling, ones that we would need to dredge every year to keep them open. The U.S. Army Corps of Engineers is also evaluating this technique extensively at projects in Barnegat Inlet and at Cape May's 7 Mile Island. They refer to this technique as engineering with nature. Another old school technique that the Corps is experimenting with is using sand to create habitat islands. The dredged sand is simply free pumped onto the low-lying marsh or on the edge of an eroded island to create isolated patches of habitat suitable for birds or other wildlife. Because our beachfront is so highly developed, these areas are very rapidly colonized by a variety of threatened and endangered species. I'm particularly excited about this habitat mosaic idea because it has the potential to provide me with a number of small sites where, working together with wildlife managers, I would be able to return periodically to add more material, maintaining both habitat and navigability. We're also considering the idea of island creation. These islands would not only provide new habitat, but could also increase storm resiliency for coastal communities. You might say it's a no-brainer. However, there's always a constituency in New Jersey, and the constituency of concern here are those who prefer open water habitat or bottom sediments for shellfish. Speaking of storm resiliency, there are thousands of acres of wetlands surrounding our coastal communities, and these marshes have been shown to be a critical aspect of coastal defense against storm damage. Recent research has shown that marshes must receive a regular replenishment of sediment in order to keep up with sea level rise. Otherwise, the marsh grass dies off, and the marsh platform itself sinks and eventually becomes open water. Traditional dredged material management techniques that remove sediment from the ecosystem actually prevent this natural accretion just when the marshes need it most. Recently, the Office of Maritime Resources, the DEP, and the U.S. Army Corps of Engineers have been evaluating the use of dredged material to elevate marsh platforms and stem erosive losses. This is best done with fine-grained material, and the slurry can often be placed directly onto the marsh. You may have heard of this as thin layering. I prefer to call it marsh enhancement, because the idea is to restore the marsh to an elevation, not dispose of dredge material. But I do get that. Enhancement usually needs, the marsh enhancement usually needs fine-grained material. However, coarse-grained material is often part of these projects too. That coarse material can be used to restore or enhance dunes, either on beaches or at the shoreline of the marsh, providing a protective edge from the battering of wind and waves. This technique is not inexpensive, but it may provide us with a more dependable long-term management option simply because of the vast amount of marsh that we have. The challenge that we have is to design and deploy efficient systems to distribute the sediment slurry to the areas that need it without overfilling and without damaging the marsh in the process. Taking this idea to the next level will be to use dredge material to restore lost marshes and stabilize the shoreline. Areas like this one in Cape May have experienced considerable damage, with many acres of marsh having been converted to open water. If left unchecked, our coastal communities will be in jeopardy, increasingly, from storm damage. This technique suffers not only from high cost, but typically involves some sort of hardening of the shoreline. And while hardened shorelines are a matter of course in our ports and harbors, they are not natural or desired feature in our back bays. The Office of Maritime Resources is currently looking at a variety of alternatives to avoid this unsightly and expensive technique. As you can see, we at DOT have been and continue to take a leadership role in developing innovative solutions for dredge material management. However, in the long run, the cost of these techniques will not be sustained on the value of the transportation infrastructure alone. We will need to find ways to take into account the total value for coastal communities in order to justify the increased costs. Which is a good segue into our next topic, asset management. Maritime Resources has been developing asset management tools, much like a lot of the rest of you at DOT have, to better evaluate cost, condition, and to prioritize our work. One of these systems is our Waterway Linear Segmentation System, or WLS. It's analogous to the roadway straight line diagrams and is the first in the national database of maritime assets statewide. First in the nation database of maritime assets nationwide. It includes engineering data on our channels, shoaling rates, and facilities served, current bathymetry and navigability data. As an added feature to our Waterway Linear Segmentation System that as you now know, is critical to waterway management, we've also created a dredge material database that will house all of our data regarding our dredge material management facilities, sediment characterization, site capacity, draw area, materials placed in or excavated, and nearby options for beneficial use. When this is deployed, both these systems, hopefully later this year, the DIMS will include a public-facing dredge material marketplace where can be explored by their needs is available in one of our facilities. Sitting on top of these two systems is a tool we call MAMS, or Maritime Asset Management System. It queries the DIMS and the WLS databases and produces a plan for maintenance dredging. It takes into account current and future conditions, cost, and the availability of dredge material management. I like to think of it as a soft meat. The solutions that can be provided, we can set this system up to give us a solution that is either based on condition goals, how many of our channels are fully navigable, or available funding. We've got X number of millions of dollars available. And the output is designed to mimic the asset management reports generated by our highway and bridge engineers. This will give management the information needed to make smart, sustainable solutions. Since taking over the recovery program for our state channel network in 2013, OMR has managed to dredge over 1.2 million cubic yards, clearing over 50 channels and opening up 45 miles of waterway in our Back Bay area. Some of these channels have not been dredged in decades. It cost us more than $75 million to get to this point, but we're getting some of that money back from the Federal Emergency Management Agency, or FEMA. Yes, we work with FEMA too. We're hoping that our forward-looking will eventually bring costs down. And that ends my version of Dredging 101. What I'd like to do now is spend left reviewing a few case studies. First up is a channel in the New York, New Jersey harbor, which was one of the very first projects I worked on when I joined DOT in 1997. The Port Jersey Channel is a 1.5 mile long waterway, and if you can see my cursor, which I hope you can, is right here, between the Global Marine Terminal and the Military Ocean Terminal in Jersey City and Bayonne, just south of the Statue of Liberty. When I joined the office, Port Jersey Channel was only 32 feet deep. And over the years, it's been deepened 38 feet, 41 feet, and finally 50 feet. It was the largest single contract in the harbor deepening project, costing over $200 million. It provides critical expansion capacity for ever-burgeoning container traffic, houses the state's first fully isolated container terminal with dockside rail, an auto import facility, and a cruise ship terminal. It was a critical component of the harbor deepening project, not only because of the enormous economic benefits that it provided, but it's also the quickest and easiest path to New Jersey from the ocean for our newest megaships. Over the more than 10 years of construction, 5 million cubic yards of dredged material were removed. The material was all beneficially used, and most of the clean material was taken to the ocean, to the HARS, for capping, and the container was stabilized and taken upland to various local remediation sites. But almost 1 million cubic yards was used to restore habitat in an abandoned channel on the south side of the Maupiti Peninsula. The Habitat Enhancement Project was developed to provide mitigation for the expansion of the channel into the Jersey Flats, an important but isolated benthic habitat. The project not only provided capacity for dredge material, but also stabilized the existing dilapidated bulkhead and restored and expanded existing habitat in the Constable Hooks Flats. Game fish like winter flounder. The success of that project spawned one of the other case studies that I'm going to talk about in a little bit. Easily the most challenging of the Jersey project was dredging close to the century-old Passaic Valley Sewage Commission's outfall pipe. This 12-foot diameter tunnel was hand-dug from the treatment plant in Newark, under Newark Bay and Jersey City, and out into the upper New York Bay. The tunnel carries over 300 million gallons of treated wastewater every day. The issue for us is that the pipe itself is constructed out of hand-poured, unreinforced concrete in short sections, with a top section held in place to the bottom simply with the force of the overbearing material. When constructed in the early decades of the 20th century, there were oyster beds in Jersey City and Bayonne. As the area developed, port facilities were built on top of those, and channels dug down closer and closer to the pipe, the crown of which lies at 61.5 feet below sea level. To make matters worse, the ground under the Port Jersey Channel was clay and glacial till, not rock. Our engineers warned us that if there was a real danger of the pipe becoming unstable if we removed too much overburden. What we ended up doing was to replace the overburden weight with 435 5-inch thick, 15-ton steel plates laid carefully and precisely 50 feet below the surface of the water on a bed of crushed stone at a cost of over $13 million. But considering that replacing the outfall pipe from Newark would cost us in excess of $1 billion, we thought that was a pretty good deal. The next case study I'd like to share is Shark River. This project was a significant challenge, mostly due to the lack of disposal options and significant shore development. There's barely room to move in this part of New Jersey, say nothing about managed dredge material. The state channels had not been maintenance dredged since the 1980s. The Shark River Basin is naturally shallow, only a few feet deep at most, and while stakeholders had been arguing over potential solutions, the channels had continued to fill in. Superstorm Sandy made a bad situation worse, and the channels essentially became impassable. Our solution was to take the very two small parcels of land, one a parking lot at the Belmar Municipal Marina, and the other a public park sandwiched between a residential development and the highway, to dewater the dredge material, using a combination of passive and mechanical techniques, and to haul that material away to the Monmouth County Waste Recovery Facility in Tinton Falls to be used as landfill cover. The mechanical solution was used extensively in Season 2. I know it sounds like I'm getting out of order, but I'm not, and was composed of a series of hydrocyclones and belt filter presses. The hydrocyclones removed the sand, and the belt filter presses dewatered the fines. Polymers were added to facilitate flocculation of the fines and accelerate dewatering. The water was returned to the bay and carefully monitored for contamination and suspended sediments, since Shark River Bay is under a total maximum daily load, or TMDL, for several contaminants. Most of the material was hauled to that landfill, but a small amount of high-quality sand was used to replenish an adjacent public beach. In the first and third seasons, we deployed geobags to dewater the material passively. Initially, this solution was only intended to be a backup plan, but contractual delays shortened Season 1 to only a few weeks, providing insufficient time to mobilize the mechanical plant. And since the permits prohibited us from dredging between January and June to protect winter flounder and anadromous fish, the material would have a chance to dewater before the mechanical equipment had to be set up. So we took advantage of what time we had. As it turned out, we were unable to complete the project using the mechanical dewatering equipment in Season 2, and the parking lot was not going to be available for another season. So in order to finish the project, we mobilized geobags again to a bigger scale at the Seaview Island Park. Most of this material was again taken to the landfill, but some was left behind at the request of Neptune Township, and they're going to use it for a shoreline stabilization project. The last project I'd like to share with you is the restoration of a dredged hole in Upper Barnegat Bay. Again, this area is highly developed, and there's no available options to manage the dredge material. Dredging has been deferred for decades. We identified a 9-acre, 20-foot-deep borrow pit in Brick Township on the backside of the barrier island, where that orange dot is. It says DH18. It was smack in the middle of a very productive bed of submerged aquatic vegetation, or SAV, which normally would say we don't want to have anything to do with it. But in this particular case, our evaluation of the dredged hole revealed that the circulation in it was very poor and that it was hypoxic for at least part of the year. There was very little, if any, aquatic life usage on the bottom of the hole. By filling the hole, there was good reason to believe that the area would become similar to the surrounding bay bottom, and given the potential to increase the habitat for valuable SAV and the associated marine life that goes with it, convincing the resources agencies to let us fill it up with dredge material and restore the bottom was not hard. So we contracted with H&L Construction, and they dredged over 200,000 cubic yards of material from 10 channels to fill the hole using mechanical dredges at both ends. Given the existing SAV bed started right outside the hole, we had to install a mile of turbidity curtain to ensure that dredge material did not smother the plants. And we also monitored that turbidity both inside and outside of the curtain at both ebb and flood tides daily to detect any plumes that might be generated. What we found was that wind and waves actually resuspend way more bottom sediments naturally, much more than our dredge did. There was no evidence that dredge material was even getting down out to the curtain, say nothing about outside into the SAV beds. So we took the curtain down in season 2 and continued to monitor the turbidity. In very few cases did the turbidity observed around the operation exceed our permit requirements, which were 1.5 times background. We finished this project up earlier this year, and we'll be monitoring the success of the restoration over the course of the next 3 years, looking at SAV, water quality, and benthic organisms. In the meantime, we have started work restoring another dredge hole in Lavalette, just south of this one. Dredge hole 25, as it's known, will hold as much as 250,000 yards of material. And permits are pending on another hole in Atlantic City known as dredge hole 86, with a capacity of almost 700,000 cubic yards. At present, we have 4 projects underway: Beach Haven and 3 CDFs, Ludlam, Story, and Gateway. We have another 4 scheduled for this fall at Good Luck Point, in Toms River, down in Lakes Bay in Atlantic City, and Brigantine. These will open up another 25 channels and remove another 230,000 cubic yards. And we aren't slowing down. We have another 57 channels in the pipeline now and several new technologies to be explored. We're working extensively with stakeholders to take advantage of opportunities and to ensure that we take community preferences and priorities into account as best we can. There's every indication that we'll meet our goal of 2024 for completion of Superstorm Sandy recovery efforts. It's our long-term goal to have a proven and sustainable program that will keep New Jersey's marine transportation system in a state of good repair for years to come. And that's quite enough for me. Thank you for your attention. I hope that this whirlwind tour was helpful. I'll now answer any questions that you have as best I can. Gabe?
All right. Thank you very much, Scott. That was a wonderful presentation. Now we're going to turn to the question and answer portion of the webinar. Just a reminder to everybody, if you do have questions, please use the chat pod or the Q&A box to send them in to us. So, Scott, the first question we got was, what quality controls are there for material to be taken off-site to be scanned for contaminants before being reused?
The sampling and testing regimen that Dredged Materials put through in New Jersey is probably one of the most stringent in the country. There's an extensive list of contaminants that are evaluated, and that list depends somewhat on where you are in the state and is determined by the DEP. They have particular contaminants of concern that are, for example, there's more of them in New Jersey Harbor than there are in the back bays of New Jersey, down the Atlantic shore. So it depends, but that testing involves not only testing the bulk sediment, but also the water, also a mixture of sediment water. A lot of different tests that can be done. We also, if the material is going to be stabilized and placed upland, there are bench scale tests that are done mimicking the stabilization process in the lab with the raw sediment, and then subjecting it to leachate tests. So I'd say it's fairly extensive.
Yeah, and this is almost a follow-up question, but how are the benefits of dredging measured in regards to reducing pollutants like PCBs? Doesn't dredging also stir up contaminated riverbeds back into the water?
Well, it can. Certainly that needs to be evaluated carefully, and it's part of the reason we do testing up front, is to make sure that whatever we're doing down there is not going to result in a pollution event. That's something very cognizant of, and the permitting agencies are taking into account. Now, when you hear about dredging, there's really 2 kinds of dredging. There's navigational dredging and there's environmental dredging. So navigation dredging is about digging the channels. Environmental dredging is about removing contaminated sediments. So if you look at a project, let's say the Passaic River remediation that's going on in Newark and north of Newark on the river, that job is not a navigation job. That is strictly to try to remove the pollutants from the bottom and restore the habitat.
Excellent. Where in New Jersey are island creations being considered?
Right now, there's a group that's being led by the U.S. Fish and Wildlife Service to evaluate islands in potential islands in Barnegat Bay.
Okay. And Another question just came in. NJDOT is building new embankments and walls throughout the state. Have you considered using the dredged material in those projects, and is it possible to transport them?
We have evaluated it. We've looked at it not only for sound barriers, but also for, for ramps and other structural potentials. And right now, the biggest barrier is the cost. The further you have to transport it and the more you have to work the material, the more expensive it gets. And straight fill is oftentimes more inexpensive and more easy to schedule than a dredged material. Because in order to get a transportation or a highway project and a channel project to line up, takes an awful lot of coordination. Highway projects take years. Channel projects may have to be done, within a couple of years, from conception all the way through to project delivery. So it's been very difficult to get us to coordinate both budgets and schedules to do it, but it is theoretically possible, yes.
How do you verify the required depth for dredging once it's completed?
Well, we would determine the required depth of dredging before we did the dredging. And that is pretty much already been determined for the entire state. It could be changed if all of a sudden there was a change in the kinds of vessels that needed to use the channel. For example, in New York Harbor, where we just recently completed a 50-foot job, and the Port Authority has announced starting studies for a 60-foot channel. That's based on the size of the vessels that want to come into the New York Harbor delivering goods. So if the vessels that are coming in can't get through at the design depth, then it needs to be deepened.
Okay. And I see one more question. Are dredging projects continuing during this COVID-19 phase, and can workers maintain safe social distancing on projects?
Well, I hope they're maintaining safe social distances. I haven't actually been out there to look at our projects, but yes, our projects are still ongoing. The governor has allowed construction projects to continue, especially the public construction projects. So I am, they're all well aware of what our policies and procedures are, and I'm sure they're following them. Our inspectors are on site every day, making sure that all the proper policies are being followed.
All right. Excellent. That's it for the questions. Thank you again very much, Scott, and I'm going to turn this back over to Diane.
Okay, thank you. All right, before closing out today, we want to thank Scott Douglas for presenting on today's webinar. Thank you, Scott, so much for taking the time out to present for us today. You certainly gave us a great presentation and definitely a great learning experience. So again, thank you so much. And we also want to thank everyone for taking the time to attend and for all your questions. We hope that you also enjoyed the presentation and learned a lot from it today. On another note, please don't forget to fill out and submit the feedback survey form for today's event. It should be available to fill out after the webinar is closed. And one more thing. Please note that we also have plans for holding another Lunchtime Tech Talk webinar. It'll be on evaluation of precast concrete pavement systems. And this will take place on June 10th. So look for an announcement for registration within the next few days or so. So again, thank you all again for attending this webinar today. We hope that you and your family and friends stay safe and healthy. Thank you very much and have a good rest of your day. Thank you.